Hey, Swati here. Welcome back to Python, Zero to Expert. This is the expert track, and today's a big one. Property-based testing. Now, don't worry if you've never heard of it. We're going to build the idea from scratch, with a picture in your head first, and only then touch any code. By the end, you won't just know it, you'll get it. Here's the promise. Instead of handwriting test after test, you'll state one rule and let the computer invent hundreds of inputs, trying to break it. Let's start with a story. No code yet. Picture testing a lock. You grab the 3 keys you can think of and you try each one. None of them opens it. Great. You call it secure and you walk away. But then a burglar comes along and tries a key you never even imagined. And it opens. That, right there, is ordinary testing. You only ever check the handful of cases you thought of, and the bugs live in the cases you didn't. Property-based testing fixes exactly this. Instead of guessing keys, you state the rule. Nothing but the real key should open this lock, and you hand a machine 1,000 keys to try, hunting for the one that breaks your rule. Now bring that into code. Back in school, you checked. Double of 2 is 4. 1 case, 1 point. That's an example test. You pick the input, you check the output. A property is a completely different thing. It's the whole rule. Double any number, and the answer is always even, not just for 2. For every number there is. So, here's the shift. Stop hand-picking inputs and checking outputs. Start stating a rule that must hold for all of them, and let the machine find the one input that breaks it.
Liam here. That phrase, for every input, is the whole game. An example test asks, does it work for this one? A property asks, does it work for anything? A much scarier question, and much better test.
Here's where we're headed. 5 parts. The core idea and how a failure shrinks down to something tiny. The property patterns. Templates for what rule to write. The strategy library, your input recipes. Stateful testing for sequences of actions. And the expert controls. Tuning, targeting, and running it in your pipeline. Let's build it up. Let's write a real complete test. Nothing hidden, this is the entire file. 2 functions to row joins a list of fields into one line, with commas from row splits that line back into fields. And then a normal test. Take A and B, send them on the round trip, join and split, and check we get A and B back. This is exactly the kind of test you've written before. You picked the input, A and B, and you checked the output. Run it with pet that one passed. Green tick, done. Feels safe, doesn't it? But pause for a second. We proved one thing. It works for A and B. The exact case we happen to think of. Every other possible input? Completely untested. That's the trap we're about to escape. Now the tool that flips all this, a library called hypothesis and its main piece given. Follow the flow left to right, because this is the part people trip on. On the far left, a strategy. Text, a recipe that makes random strings. Wrap it in lists, and now you've got a recipe for random lists of strings. Then, given. And here's the key idea. Given is a decorator. It's the line with the @ symbol that sits on top of your test function. Its whole job is to take that recipe, generate an input, and call your test with it. Again and again and again. Hundreds of times, each with a brand new value.
Liam, if decorators still feel fuzzy, a decorator is just that @ symbol line stuck on top of a function that quietly changes how the function runs. Here's the mind bender. You don't call your test yourself anymore. Given calls it for you once for every input it generates. That's the whole trick.
Now here's the property, and we'll read it one line at a time. Up top, we import given and the strategies module as st plus our 2 functions. Then the decorator, given, Handed lists of text. That is the piece that feeds inputs in. The function takes one argument, fields, and fields is a single generated input, one random list, filled in by given every time it calls us. Inside, we do the same round trip as before. And the last line is the rule. For every field's hypothesis throws at us, the round trip must give it back, unchanged. Notice, we never wrote one specific input. We described the rule and the shape of the data and handed the rest to the machine. And this is what given actually does. It calls your one test over and over, each time with a different fields, an empty list, a couple of words, some strange Unicode, and eventually, that one. A list holding a single comma. You would never type that by hand. Hypothesis will. And there it is. Hypothesis doesn't just say failed. It hands you the exact input that breaks you. A list holding a single comma. Here's why it breaks. A field that is itself a comma gets joined into a string that's just a comma, and splitting that back gives you two empty strings, not your one field. Silent data corruption. And here's the magic word, shrinking. Hypothesis hit lots of failing inputs, some huge and messy, then automatically whittled them down to the smallest one that still fails. A single comma, nothing left to distract you from the real bug. So, what rule do you even write? Good news, there are patterns for this. And the first is the one we just used. The round trip. Anything you can undo. Here, using the JSON module, dumps turns the list 1, 2 into text, and loads turns it straight back. Encode, then decode, must land you exactly where you started. Save, then load, compress, then decompress. All round trips, all the same shape. Second pattern, invariants. Things that stay true no matter what. Sorting can't invent or lose items, so two things never change. The length, sort 3, 1, 3, and you've still got 3 items. And the contents. The set of values is identical, just reordered. When you can't predict the exact output, assert what survives the operation instead. That's an invariant. Two quick ones. Idempotence. Doing it twice is the same as doing it once. Sort an already sorted list, and nothing moves. Cleaning and deduplicating work like this. And commutativity. Order doesn't matter. The bigger of A and B equals the bigger of B and A. If your code is supposed to have these properties, assert them. And hypothesis will try hard to prove you wrong. And the most powerful pattern, the oracle. Your real function is fast and clever, and you don't fully trust it. So you borrow a second version that's slow, but obviously correct. Here, Python's own built-in sum. Then you assert the two always agree on every input. If they ever disagree, one of them is wrong, and hypothesis finds the case that proves it.
Liam, the trap with oracles, don't build yours by copying the function's own logic, or you'll just paste the same bug into both, and they'll happily agree while both being wrong. The oracle has to be right by a genuinely different, simpler route.
Everything starts with a strategy, a recipe for inputs. Integers gives you whole numbers, including 0, negatives, and enormous ones. Floats gives decimals, and the nasty ones too. Infinity and not. A number. Text gives strings, empty, emoji, full Unicode. There's booleans, lists of anything, sampled from, which picks from a set you handed, and dictionaries. Each one deliberately reaches for the edge cases you'd forget to try. And you combine them. The pipe means either an integer or a float. You can bound them. Integers from 0 to 10. .map transforms every value. Integers mapped times 2 gives you only even numbers. And .filter keeps the ones you want. But be careful with filter.
Liam, with the trap I see most. If you generate any integer and then filter down to evens, hypothesis throws away half its work and may warn you it can't keep up. Shape the data at the source with map. Don't filter it at the door. Cheap habit, big payoff.
When your data is a real object, build your own strategy with the composite decorator. It hands you a draw function. Call it to pull a value from any strategy. Draw a quantity, 1 or more. Draw a price, 0 or more. And never a not, a number. Then return a real order. Now the given decorator uses orders. And every test gets a valid, sensible order. Never a negative price. Never a broken object. You're generating your own domain now, not just numbers. Often you don't even need composite. Builds takes your class and a strategy per field, and constructs the objects for you. Hand it order, a quantity, and a price. And it's done. And from type goes one better. Give it a type, and hypothesis reads your type hints and infers a strategy automatically. For a well-typed codebase, that's almost free test data. And there's a whole extras package for the data world, testing numerical code. Hypothesis.extra.numpy generates arrays. Pick a type and a shape, and outcome random arrays, integer overflow, and all. Here, transposing a 2x3 array twice must give back the original shape. An invariant on real matrices. There's a pandas one for data frames too. If you work with data, this is where property testing truly earns its keep. Single inputs are one thing, but the nastiest bugs hide in sequences. So, hypothesis can drive a whole state machine. You mark methods as rules, add pushes a random integer and counts it. You mark checks as invariants. Count agrees says the number of items must always equal the number you added. Then hypothesis generates random sequences of these actions. Add, in orders you'd never think to script, and it rechecks the invariant after every single step. That last line turns the machine into a test your runner finds automatically. Here's the expert move. Test your real system against a simple model of it. We're checking a key value store. A plain dictionary is our model. Obviously correct. A bundle remembers the keys hypothesis generated, so later rules can reuse them. The put rule writes to both the real store and the dictionary. The get rule asserts they always agree. Hypothesis then drives thousands of put and get sequences. And the instant your store disagrees with the simple dictionary, you've found a real bug.
Liam, this is exactly how people test databases, caches, and AP is for real. Write a dead simple model of what it should do, then let hypothesis pit the real thing against it with random sequences. It finds ordering bugs no example test ever would.
Settings is your control panel, and it stacks right above given. Max examples turns the search up. 1,000 inputs instead of the default 100 when you want a deeper hunt. Deadline none switches off the per example timeout, which matters for slow functions. And derandomize makes every run use the same inputs, so a green build stays green in continuous integration. 3 ways to nail things down. The example decorator pins a specific case that once broke you, checked on every single run forever, right beside the random ones. The seed decorator makes a run perfectly repeatable when you need it. And for free, hypothesis saves every failure it finds to a small local database and replays it first next time. So a bug you fixed can't quietly creep back in. Sometimes pure randomness isn't enough. You want hypothesis to hunt toward the failure. That's target. You compute a number that measures how close you are to breaking. Here, the floating point error between two ways of adding the same values, and you call target on it. Now, hypothesis actively steers its inputs to make that number bigger, and closes in on the extreme cases far faster than luck ever would.
Liam, reach for target when there's a natural dial to push, a rounding error, a queue length, a load factor. If there's no meaningful number to grow, plain given is perfectly fine. With two traps that quietly waste property tests. 1. Writing your oracle by copying the function's own logic. You just duplicate the bug, and both sides agree while both are wrong. The fix is on the right. Compare against a genuinely simpler, independent version. 2. A property that isn't deterministic, one that leans on the clock or on a set's ordering. It'll flake and you'll blame hypothesis. Keep properties pure and keep oracles honest.
You don't even have to write the first draft. Hypothesis ships a Ghostwriter right on the command line. Tell it that JSON dumps and JSON loads form a round trip, and it writes the property test for you. Tell it sorted is idempotent, and it writes that one too. It's the fastest way to go from an untested function to a real property test. You read it, tweak it, and keep it. Sarah here with how this lands in a real project. First, you don't throw away your example tests. You keep them, and you add properties on top. Second, the fix for our comma bug. Swap the hand-rolled join for a real serializer. JSON dumps turns the list into text. JSON loads turns it back. And now the round trip holds for every input, commas and all. Wire this into your CI, and every pull request gets fuzzed with fresh random inputs automatically. And this isn't academic. Property testing found 23 real bugs in a production database engine, and its inventor found hundreds more in car software and in Dropbox. Your code proves itself. And that's property-based testing from the ground up. You've got the intuition now. State a rule, and let the machine hunt the one input that breaks it. You've got the patterns, the strategy library, custom and stateful testing, and the expert controls to tune, target, and reproduce. Here's the rule of thumb to carry away. Anytime you can name a truth that should always hold, write it as a property, and let the machine try to prove you wrong. That's real expert testing. I'm Swathi. This is Codecraft. See you in the next one.